Hello and welcome to another lesson on GCSE physics. Today's learning intention is to know what an isotope is. For the Do It Now task, which is a recap of the first lesson on this topic, I would like you to complete the table below to show the particles that make up an atom, including their location within the atom, the relative charge and the relative mass of the particles. Pause the video, copy and complete the table, and then press play to mark your work. So, protons then, we've been told in the table already that they're found inside the nucleus, which is great. However, they have a relative charge of +1, which I hope you got correct. Now, it has to be plus, don't just write a number 1 and assume that the examiner knows you mean plus. Make sure you specify plus, because charges can be positive and negative. The relative mass can just be written as 1, because mass doesn't have positive and negative, mass is just mass. Now, neutrons are also inside the nucleus, nice and straightforward. However, their relative charge is 0 because they are neutral. They have the same mass as a proton, so the relative mass is 1. And then finally, the third particle, which I haven't named, there is the electron. Its location is that it surrounds the nucleus in shells, or you could have said it surrounds the nucleus in energy levels. I've told you its relative charge is -1, but its relative mass is 0.0005, or 1 divided by 2000 as a fraction. The success criteria for today is to know what an isotope is, to know how to handle a radioactive source safely, and to calculate the number of protons and neutrons in an atom. Scientists wondered why some atoms of the same element were heavier than others. For example, you could have helium in one batch that weighed heavier than helium in another batch. And obviously you would expect all the atoms of the same element to have the same mass. Now, James Chadwick, who was working with Ernest Rutherford in 1932 after he completed his PhD, actually was able to solve this problem. I would like you to use your knowledge that you've gained in the previous lessons to have a go at thinking about how he could have done this. Pause the video, write down your answer, and then press play. So, James Chadwick did this by discovering neutrons. The reason that different atoms of helium had different masses is because they had inside the nucleus different number of neutrons. The fact that they all had the same number of protons made them still all be helium, but because they have different neutrons, they have different weights, and we actually go on to call these isotopes. Now, it's probably worth mentioning at this point that James Chadwick started out as a shy boy, raised by a working class family in Manchester, and he went on to solve one of the biggest issues of the time in physics, probably in science, to be perfectly honest, showing great ambition, starting from really humble beginnings and then working his way up to working for a very, very well respected scientist and solving a major issue of the time. So, this discovery of neutrons by James Chadwick then basically presented also the discovery of isotopes. Isotopes of the same element always have the same number of protons but a different number of neutrons. Now, at the bottom of the board there, I've shown you 3 isotopes of nitrogen. Now, you might remember from your studies at Key Stage 3 that the bottom number there is the number of protons. So each of those 3 atoms of nitrogen have 7 protons in them. However, that top number is the number of protons added to the number of neutrons. So because that number is different for each of those 3, that means they all have a different number of neutrons, so they are different isotopes of each other. Now, what is important, and Rutherford had already made use of this, is the fact that some elements are actually, or some isotopes rather, are actually radioactive, which means that they give off radiation. And so what we can do now is have a look at a demonstration to look at how to handle a radioactive isotope safely and to see what experiments we can do to find out information about radioactive isotopes. So let's look at how we handle a radioactive source safely. First of all, we should note that it is stored in a lead box. Now, when we take the source out of the lead box, we have to handle it using long arm tongs to make sure that we avoid direct contact with it. You can see me here taking out using those tongs. Now, we also want to limit our exposure time, so after we've finished using it, we put it back in the box as quickly as possible to make sure that we've been exposed to it for as little time as possible. Now let's look at how we set up the equipment so that we can do things with the radioactive source. This blue device here is called a Geiger counter, and we use it to detect particles of radiation. I'll turn it on in just a second to show you that it actually counts radiation even when we haven't got the source. I've set the equipment up here though, so that when we actually get the source out, it won't be pointed at myself and it won't be pointed at anybody else in the room. I've turned the Geiger counter on here. It started on 0. If we start it actually clicking in just one moment, there we go. We can see that straight away it actually starts to detect radiation. That is because there is background radiation in the atmosphere anyway. Now I'll get the actual source here. So like I said earlier on, we're going to handle it carefully. It's stored in a lead box, and we'll open that lead box now, and we'll get some long arm tongs to lift out this source, which is a gamma source incidentally on this occasion, and put it there. Now I'm going to put that into this setup, making sure not to point the gamma source at anyone. I could do it using the tongs, but I think I will just pick up the source now using the mould that it's going to be clamped to. There we go, and then I'll put it back in. Now what you should notice, if you look at the Geiger counter on the right hand side of the video, you can see that the number of counts now is increasing quite a lot because the Geiger counter is detecting radiation being emitted by the source. Now we can use this setup to actually look at lots of different properties, like how far the radiation can travel and what things the radiation can and can't get through. Okay, so we've just seen how we would set up the experiment and how we would handle isotopes safely. We can now look at a quick summary of the findings from this. So the observations of the safety procedures that we've just made, we have to handle with tongs to avoid direct contact with the source. We wouldn't want to touch it because then we would become contaminated. We also should limit our exposure time, which basically means when the source is not being used, we should put it back in place in box. We have to store it in a lead box. The reason we store in a lead box is that the radiation cannot get through lead, and so therefore it should be safe for us. And then finally, we don't point the source at ourselves or at anybody else. Now, I know I didn't show you all three of those sources during that demonstration, but there are actually three different types of radiation that we have sources for in school. They are alpha, beta and gamma. Now, we detect alpha radiation using a Geiger counter. As I showed you, that was the blue piece of equipment. And we would find that alpha can actually travel up to 5 centimetres in air. We would, however, find that if we put a piece of paper in between the source and the Geiger counter, that the alpha would no longer be detected. So therefore the alpha particles get stopped by paper, they get absorbed by it. We could have then done a similar thing with the beta. Again, we would be using a Geiger counter to detect the beta radiation, but we would have found that it could actually travel considerably further. It can travel around 1 metre in air, and it can actually get through paper as well. But to stop the beta, we have to use around 2 or 3 millimetres worth of aluminium. And then finally, the source that I actually had out for the sake of that demonstration was a gamma source. Again, it's detected using a Geiger counter. It has a range in air though of at least 1 kilometre, which is a tremendous range and something that obviously we can't demonstrate in the laboratory. It is only stopped by 10 centimetres or more of thick lead. It can pass through paper and it can pass through aluminium. Okay, now let's look at information about isotopes then. Here we've got potassium on the board. Bottom number is 19, and we call the bottom number the atomic number. The atomic number, bottom number, tells you how many protons there are. Remember, of course, the number of protons is equal to the number of electrons in an atom, so it's also the same as the number of electrons. However, if you are asked what is meant by atomic number, you should say that it tells you the number of protons. Then the top number, which is also called more correctly the mass number, is equal to the sum of the protons and neutrons in the atom. So in this case, we've got 19 protons because the atomic number is 19, And because the top number is 39, and that's protons added to neutrons, that means that when we take them away from each other, we find that there are 20 neutrons in potassium. Okay, we'd like to have a go at this task for me now, please. I've got 3 atoms on the board for you. We've got carbon, lithium and sodium. I would like you to pause the video and work out how many protons and neutrons are in each of those atoms. So let's take carbon then. First of all, the bottom number, the atomic number, is 6, meaning that there are 6 protons in carbon. The number of neutrons we find by doing the mass number take away the atomic number, so 12 take away 6 would of course be 6. If we consider lithium, lithium has a bottom number of 3, so the number of protons there is 3, and the number of neutrons, 7 take away 3, sorry, I knew what the answer was, is equal to 4. And then finally for sodium there, Na, we've got 23 as the mass number, 11 is the atomic number, so the number of protons is 11 and the number of neutrons is 23 take away 11, which is equal to 12. I hope you got all of those correct. We'll have another question later on to check that you're able to do those. Okay, I would like to have a go at this summary task now. We've looked over the previous 2 lessons at a lot of history to do with how our understanding of atoms has changed over time, beginning of course with John Dalton's model of the atom, then Thomson's model, Rutherford's Bohr's, and then Chadwick making his discovery as well. I would like you to pause the video and write a summary of how our understanding of atoms has changed over time. Now make sure to please include each of the key words that are on the board there. Obviously for some of them there's quite a lot of keywords, particularly the part about Rutherford's model of the atom as well. So include as much information as your summary as you can and then press play to continue the video. So in your summary, you should have started with John Dalton, and you could have mentioned that basically Dalton thought that atoms were tiny spheres that couldn't be divided. Then moving on to that, in 1897, Thomson proposed the plum pudding model of the atom, which is where he said the atom was a ball of positive charge with electrons scattered throughout them. Then Rutherford came along and developed the nuclear model of the atom. He did that after completing the alpha scattering experiment. He said that the atom had a positive nucleus at the centre, and then electrons surrounded that nucleus in shells or energy levels. He also said that most of the atom was made up of empty space. And then if you wanted to include the word evidence, which I don't think I did for you then, you could say that he came up with this because the alpha scattering experiment provided evidence that couldn't be explained by the plum pudding model. And then Bohr adapted the nuclear model to say that electrons orbit the nucleus at specific distances only. And then finally, Chadwick discovered the neutron, which allowed for the explanation of the existence of isotopes. Okay, let's see if you've met today's success criteria with a quick quiz. There are 3 questions here for you to have a go at. Try and get as many as you can. Pause the video, write down your answers, and then press play. So question number 1 was, what is an isotope? Well, an isotope is an atom that has the same number of protons but a different number of neutrons. You would need both parts of that answer to get the mark. You would have to say same number of protons but a different number of neutrons. Okay, question 2. 2 things that we should do to keep safe when handling a radioactive source. Lots of different things we could say. You could say don't point the source at anyone, use tongs to hold them, better to say use long handle tongs, limit the time of exposure and store in a lead box. And then finally, how many neutrons are there in nitrogen? 15. Well, the top number is the mass number, which is protons added to neutrons. We can see there's 7 protons, so we would do 15 take away 7 to get the correct answer of 8.